Last time, 5 seconds for studying using normal distribution to approximate the discrete distribution. This is one big question in Poisson distribution. This is also one of the actuarial science exam question. We have 120 vision care insurance policy, so basically 1,250 vision care. So that's our sample size. It's really large sample size. Number of claims fell by everybody in this policy follow up Poisson distribution. So the number of claims will be average of 2. And how many claims each person filed is a random number. It could be 0 or 1 or 2 or 3. Depending on the situation. As far as face vision care, I only take 1 pair of glasses a year, so for me that's probably a very average of 1, but this is mean of 2. That means sometimes you have 2 glasses per year. All right, assume the number of claims filed by different policyholders are mutually independent. Calculate the approximate probability that is total of between 2,450 and 2,600 claims will be filed, and that is a total considering all the policyholder. So this is a summation of 1,250 random variable, and so for summation, because each individual variable is Poisson, the summation also is Poisson. So this is originally a Poisson distribution question, but because the sample size is so large, we won't be able to do it with the Poisson distribution formula. Our calculator won't be able to handle it. Having an average of 120, 50, raising to the power 5, and the calculator will be exploding. So then 125 0 to the power 2,000, that's even more impossible for our calculator to do. So we're going to convert it to a normal distribution, and I use normal distribution to approximate the answer to the question. Try it, see if you're able to figure out the answer. All right, so what we're going to do is remember the mean. We're calling the y. Y will be the summation of a lot of different variables. Let's first try to figure out a way to write it out. So then we do the calculation, it will be more manageable than just numbers. Might attach some letters or variable names to make it easier to analyze it. representation is a scale of mean. So individual vision here is what we call X, right? Xi, and obviously Xi follow Poisson distribution with a mean of 2. Mean is 2. And then I here is 1, 2, 1,250 I is 50. Now here we're going to talk about total claims. So we're talking about total number of claims for this many people. So Y is the summation of all these claims. Summation of Xi, and then I is from 1 to 1, 2, 5, 0. So Y is a summation with many, many claims. And you can see because there's the additive property to the Poisson distribution, Y would also be a Poisson distribution. Right? If it's 1x, the mean is 2. If it's 1,250 x, then the summation will be 150 times 2. So that gives us 2500. So that's the mean. And we also know for Poisson distribution, the mean and the variance will be the same thing. So the mean is 2,500. The variance for Y is also 2,050. And we're trying to standardize it. So we're see the question says what's probability is between these. So we're trying to calculate probability that the number of claim, which will be integer, this integer is supposed to be between 2600 and 2450. All right. This one, because it's discrete for correction of continuity, normally we would try to do 0.5 up and 0.5 down. But I think because the boundary is in the 1,000, it doesn't really matter what you corrected or not, right? You can do it. You can do it according to the theory, should be adding to 0.5. But I think it won't change the answer by that much. Your final answer should be the same anyway, because the size of the number is so large and 0.5 correction doesn't make much of a difference. But nonetheless, we would make Y between 2,600.5 and the lower boundary will be 2449.5. I would find that number a little bit odd, right? So that's the boundary. We're gonna try to, now we're working with normal distribution, like we're trying to approximate this with a normal distribution. The mean will still be 2500 and the variance will still be 2500. This is the variance, not the standard deviation. Standard deviation, you have to take square root of it. So try to convert it to a normal distribution because the sample size is so large. So then the conversion from a regular continuous distribution, there's a change. This is discrete, this is continuous. That's why we got that 0.5 correction. All right, now we're going to convert it to a z. So z is less than, you're going to take the up boundary minus the mean. Mean would be 2,500 and divided by the standard deviation. Standard deviation is square root of variance. Remember the variance is 2,500. So the standard deviation is square root of it. Therefore, the standard deviation is actually 50. The measure will be 2449.5 minus 2500. Because this number is just so close, I think it doesn't change much to just write 2,600 minus 2,500, you got 100. 100 divided by 50, that's 2. On this end, it will be negative 1. So it's negative 1 and 2 would be easier. But if you are using those decimal point, it will change it slightly, like by a little bit. But your final answer should be pretty much the same. So when we are the other, I write the one with the decimal 0.5, and you can calculate it without the 0.5 correction. The size of the number is large, so that correction won't change our answer. All right, the rest, once you find the boundary, the two z value at the left end and the right end, you put it into like R coding, or you can put it into a normal standard deviation table for the calculation. Kara, I haven't really sent it to the testing center yet. So normally what you would do, you do it afterwards, or you reschedule for your quiz?
Like the testing center said there were.
Okay,
I checked.
okay. Yeah, so I'll submit it after class to the test. Okay, so any question for the computation? We're practicing a question about using normal distribution to calculate Poisson distribution question. The answer. All right, you can submit now if you're. Thank you. Pull a page with a run our code online. That may allow you to calculate the normal distribution faster. But if you already have the table, that works too. The table is on Georgia View. But this calculation, you can use a table or you can use online R coding to code the calculation. So how did you get your answer?
H-R.
I see. That's my habit, because I feel like I just type one command, one on the command, it's the answer. But with the table, you have to look at the row, look at the column. There's a lot of matching different numbers. Like it's easier to just go ahead and use the code. That's the calculation we're eventually converted to a question about Z. So we're using the normal distribution against the function. So far, I have 4 answers already submitted. These 4 answers are all correct. So this is a Poisson distribution question. Individual distribution have a mean of 2 because our sample size is 1,250. So the summation of those 1,250 x value would have a total of a y value. The y value is a Poisson distribution random variable. So for the y, it will also be a Poisson distribution. Writing PO for Poisson distribution. The mean will be 2,500, and we want to use a normal distribution to handle the calculation related to y. That's why I write the normal distribution with a mean of 2,500, and the variance is 2,500 as well. And that makes it possible to calculate. Yes, thank you. Made it possible to calculate the y distribution question using the normal distribution conversion. So we converted the y question to a continuous y, which is a normal distribution question, and then to a z question. That's why you see the last rule in computation about 3 variable. There's a slight change from one another. Yeah, we will be able to apply the normal distribution onto the last calculation. All right, if you are finished with this question, do you have any question over the homework? Any homework question? Andrew, I replied your email because I saw all your answers to the homework question. They're all correct. I didn't find any mistakes, but you said you were not sure, so I don't know which one.
Well, as long as there's no mistakes, yes.
Yeah, so, I have already posted the quiz. It's on Georgia View under assignment, if you don't have any question, you can go ahead and start working on those quiz question. The quiz is over 5.4, question 4. So you can go ahead and start your quiz if you don't have a question with this or with any question. But if you do have a question, feel free to talk about the question. And also try to finish up with this one if you haven't finished it. So basically, I changed the homework question slightly and made it into a quiz. You're finished with the homework. It would be very similar to what you did on the homework for 5.4. But if you didn't finish 5.4 homework, then you might have to review your 5.4 quiz. Thank you. The quiz is online. That probably means you have to have some device that goes online. If you can't go online with your own device, you might be able to use the classroom computer. But I didn't really print anything because I feel like if we're allowing us to use our coding or the computer for calculations, I might as well use your device to take the quiz and also submit quiz. It's the same. Quiz one. Do you have a device that goes online? Quiz two. We have a quiz today.
Didn't bring my computer, I have the phone.
Yeah, you can just, I think as long as our phone goes on the internet, you can go onto Georgia. It's under assignment tools. Alright, the quiz is online and let's see. You log into Georgia View under course tools assignment and you find places to submit our homework, and that's where we had our quiz one. And quiz two is right here. If you click on it, you should be able to see the question in that folder. And you can download or look at that quiz question, start working on it. It's a change from our homework, but it's a similar version of the homework question. If you have already did the homework, you will be okay. But if you run into any problem with the homework, you can ask before you take the quiz. It's right there. It's under assignment. I wonder if there's an individual app for Georgia View, but when I log on to Georgia View on my phone, I did it with the internet. I did it with a browser. So I have to find where it is. Once you finish working on them on paper, just take a picture with your phone and submit that image as your solution to this.
It's not in the board.
It won't do it.
I downloaded the file and then,
It won't open.
yeah,
It should be in files. Can you see the file on your phone?
it's saying that it's syncing, but
It won't do it. Let me show the quiz over here then. Let me show it on the screen when you finish calculating. I guess submission would be okay. Downloading and viewing is. On my side. So let me try to make sure both the question can be in the same screen. So it can be a bit larger than this. That's the first question. Trying to phrase this question in the same screen. In the same. Okay. Yeah. Okay, so
Thank you.
that's the quiz question. Right, if you also have the same issue downloading it from your phone, you can just work it on paper. And then once you finish calculating on paper, you can just hand me the paper or the answers to the quiz question. So you can do it on paper or submit it online, please. So that way, don't worry about not downloading the time. Probably find it similar to what you did on homework. Any question? Are you having issue looking at or view the problem, the quiz problem questions? Sure, anytime after class, what time would you?
Yeah.
Yes, tomorrow my office hour is at 11, the same as upstairs to 19.
Ready for this?
Did you do the homework back for? Yeah, this is like a changed version of it's the same question. Well, I guess you can also postpone. Not ready.
It's. So. Absolutely.
M is a summation, right? Already have those two. This one because summation. Oh, you have the. If you multiply it out, you will see the distribution as a coefficient. So I see. Okay, yeah, that's fine. Yeah. Thank you.
Yeah.
Are we almost finished? Do you need more time? It's close to.
Pretty much done.
I was gonna say. Do you need more time?
I'm pretty much done. I just have to submit it to the bank.
Okay. It's. You can see the question for the later half of the book tend to need more time and more advanced than what we have in the first half of the book. Okay, this is 5.4. So next Wednesday, we should be having a quiz over 5.5 and 5.6. I'm probably gonna choose one question from 5.5 and one question from 5.6. In the meantime, we are up to section. We're up to section 5.7. So with the time left, I'll start talking about 5.8. But if you need more time with the quiz, you can continue work on it. I wish to at least try to finish chapter 5 today. So next week we can move on to chapter 6. All right. The whole chapter 5 has 9 sections. So we are pretty much talking about relation with variables and moving on to possible connection with normal distribution. The other 4 sections. The first 4 sections work on relation and how we combine several variables to a single new variable to simplify or streamline the calculation. All right, so 5, 5, 6, 7, 8 is in relation to a normal distribution or in focus of the average value, the center of the distribution. All right, last time on Monday, we worked through 5.7. 5.7 is application of normal distribution on discrete case. We can use normal distribution to approximate binomial distribution and Poisson distribution. The reason we wanted to do it is because for binomial distribution and Poisson distribution, when the sample size is large, they tend to pose some calculation difficulty. So when it's hard to do it one way, we search for a way to do it the other way. Normal distribution is an option. So for binomial distribution, we study the relation and realize binomial distribution can be considered as a summation of several Bernoulli variables because it's a summation of identical variable. We're able to look at it from a normal distribution standpoint because it's an application of central limit theorem. So converting a normal distribution variable, binomial distribution variable into a normal distribution variable, we are able to identify its mean and variance and then calculate it by converting the question into a z question. And this is the relation from a discrete distribution to a continuous distribution. We have to do what we call a half unit correction for continuity. a comparison between the discrete graph, which is all the bars of the histogram, to a normal curve. You can see the higher the sample size is, the more similar the discrete distribution to a continuous distribution. All right, we had a couple examples on Monday to study how do we find out the probability related to binomial distribution using the normal distribution solution. So down here is a calculation using binomial distribution formula. Up there in the middle is a calculation using the normal distribution method. You can see the normalizing process. Now we determine the z-value, use the z-value, we determine the probability. And there's a couple more examples on that sense. Right, and then again, for Poisson distribution can also be considered summation of several small Poisson distribution, which makes sense that a normal Poisson distribution can be standardized. The y is a Poisson distribution, the lambda is a mean, so root of lambda will be the standard deviation. So we're doing variable minus mean divided by standard deviation. This is standardizing process converted to a standard normal distribution, and then we can calculate anything related, any probability related to the y, using the W. So that is an example on the Poisson distribution using normal distribution method. Those are the assignment for 5.7. Monday we did a little exercise. One of the assignment is question 2. It's an even number question, so I thought I should work it out as examples so you can see how it's being calculated. We got 25 binomial distribution. The probability is 20%. We're trying to calculate the probability. The x variable is between 2 and 9. Okay, so in this case, the sample size is 25. So number of success is between 0 and 25. We want to find out probability for to be between 2 and 9. So the first method will be using the binomial distribution formula or using the binomial distribution table. Here is, right, this is the analyzing. The question looks for a boundary at 2 and 9, but 2 and 9 is not included. So we convert it to a discrete case because we're looking for a variable between 2 and 9. So x takes on 3, 4, 5, 6, 7, 8 because it's discrete. Right, so the table 2 in the book is called the binomial distribution table. It's a cumulative distribution table. So all the number in the table represent probability to the left of a given value. So we had this table, the binomial distribution table when the sample size is 25. Those are the x value. It goes on to 25. We only need this portion of the book of the table. So for that question, we're studying probability of x being between 3 and 8, actually. 3 and 8. So to calculate this one, we need this boundary, which include all the probability below 8, including 8. And this number is all the probability below 2 and including 2. After we subtraction, we find out probability for summation of 3, 4, 5, 6, 7, 8. Then let's just try to isolate the number in the table in order to find the probability. So that's the exact answer to the question. The second part of the question, I didn't do it. I did it on the board using the central limit theorem. So what we're going to do is to find a boundary, which is this boundary, 9 is not included with the 8.5. 2 is not included with the 2.5. So we take the 2.5 and 8.5, standardize it, and find the solution. Right, I didn't include it over here. Any question for 5.7? I'm just trying to briefly talk about it because we went through them already on Monday. So today we're going to talk about Chebyshev theorem. The title is called Chebyshev Inequality and Convergence in Probability. So as indicated by the title, the Chebyshev theorem is not an equation, it's an inequality. So it will be providing an upper bound and lower bound. It's not going to provide the exact value of the probability. Okay, so what exactly is probability? According to a discussion in the book, the Chebyshev inequality will show that the sample mean is a good statistical estimation of the population mean. And also you can extend that idea in the Chebyshev theorem to binomial distribution, or the binomial probability y over n. We can show that y over n is a good estimation for the proportion p. So we are already talked about a couple of estimation. We said sample mean, X bar, is the estimation for the population mu. The sample variance S square is a approximation for the population variance sigma square. Now here we're saying Y over N is an estimator or a statistical estimate for the proportion of P. So here, this section will kind of illustrate that process in probability sense. All right, so let's start with what exactly is Chebyshev inequality. So here we are. So what is Chebyshev inequality? It really is a very useful inequality which apply to any random variable. And let's make it more general. Central limit theorem only apply for larger sample size. And we have empirical rule only apply to normal distribution, but Chebyshev theorem is true for any random variable, which make it really interesting. But then also it has a limitation in the sense it doesn't provide any equation, it's inequality. And notice that the equality is in like a butterfly format, and like this is a bigger than, this is a less than, so it's kind of like a match. If you write your equality like this and this, it has to be wrong. So it can be this and this, or it can be this and this. It can be a pair, this way or this way, to make sure these two are opposite when you're writing your equality, so that you don't accidentally put in the wrong sign and to equality. So what's the meaning of the Chebyshev theorem? If you read it, it says probability, it's a probability inequality. It says probability that X, any random variable X minus a mean for X. So this is variable minus the mean. All right. Most data will behave around the mean, some less than mean, some more than the mean. So here we're saying the distance between the random variables and the central distribution, that distance, how likely for that distance to be larger than the key times standard deviation? The answer is very small. All right, so X minus mu to be larger than a certain number times the standard deviation. This probability is smaller than 1 over k squared. So we're trying to indicate that most of the data will be spreading around the mean, and outside that boundary, we won't have much. So if you think of it, basically Chebyshev theorem, that's supposed to be our mean, right? But that's the mean. This is the center of the distribution. So where is our X? X in here, 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 but here. So this is our X data number line. So we're saying most of this, right? So most of it is right in the middle. This is what we're saying X is between mu plus k times standard deviation and bigger than mu minus k times standard deviation. Basically, the middle within this boundary is when X minus mu has an absolute value less or equal to k times standard deviation. These two inequality are representing the same thing. The bottom one is representing the inequality using absolute value notation. The top one is really indicating the left endpoint, mu minus standard deviation, the right endpoint, mu plus standard deviation. So we're saying majority of them are here. Now, how likely for the random variable X to fall outside this boundary? Very little. So little that it is smaller than 1 over k squared. Suppose k is a larger integer like 2, 3, 4, then 1 over k squared is a small likelihood, small probability. So that's basically saying to be bigger than this, very small chance. That also means that the opposite, to be less than this k times standard deviation, meaning that to be in the middle, the chance is very big. So the inside of these two boundaries, the probability is 1 over k squared. You see this more often in many of statistical books. Outside this part and this part of the area, you can see the area is small. The area is less than 1 over k squared. We do not mean it's equal to 1 over k squared. We mean it's less than. It's the actual probability depending on the original distribution. Since we do not know the distribution for the X, then the true probability outside the boundary, it varies from one another, but we know at least it will be smaller than 1 over k squared. So it's pretty small. All right, so that's really the meaning of the Chebyshev theorem. Right, so we're going to try to prove it. And since it's an interesting result that apply to any random variable. So how do we prove it? We try to put the probability into a calculation of expectation, because in an expectation you will need probability for small and for probability for big. So here we're trying to look for probability that this is larger than k times standard deviation. So here we're going to put it into a perspective. We are assigning a set that says all the number x minus mu bigger than k standard deviation. We call that set A. All right, so when you're trying to calculate expectation, you have to do, so this is how we calculate expectation of x minus mu squared, which really is a definition for the variance. A equal to summation x minus mu times the probability for x. This x is for all the possible x's in the domain. Now we're going to try to separate this s into two, the one that's in A, the one that's not in A. So the one that's in A is here. So you're going to have to, this is a big summation. We're going to write it into two separate summation. One part of the summation is a variable times the probability. It's part of the calculation for the expectation when x is in A. Now here is when the x is not in A. A prime is not in A. So obviously, if you want to calculate variance, you have to add both of them. So naturally, if you skip one of them, let's say we don't calculate this, right? That's positive, that's positive. If you get rid of this part, you're making this smaller. So we know that this summation of the two is bigger than when you have only one. So we know the variance is bigger than this summation. The summation only taking over all the x value when it's in A. I hope that kind of makes sense. So your x may have 5, 4, 3, 2, 1, 0, 1, negative 1, negative 2, negative 3. Now you're only looking at inside the A, which will be 5, 4, and then negative 5, negative 4. All the middle one is gone. Opposite set. So we're calculating on a small set. We know this is definitely smaller. So what does that mean? And then we have this idea, since inside A, all the x minus mu is bigger than k times standard deviation. So now we have x minus mu, and we know inside A is bigger than k times standard deviation. We do a substitution. We substitute this part by k times standard deviation. That's why we're making it smaller. So this is bigger than, that is bigger than k times standard deviation times f of x. And then there's no longer having any x in this notation become a common factor. We bring that outside. Right, and then what's interesting is that now you have standard deviation on the left and standard deviation on the right. We cancel that. We have this thing that this set is less than 1 over k squared. So after cancel the standard deviation from both sides of the equation, we end up having this. This is less than 1 over k squared. Now this is a summation of probability, which essentially is this summation f of x, x belongs to A, is the probability for like probability of A. And what is A is that set. So this is probability of A, therefore this is probability for x bigger than mu, or x minus mu bigger than k times standard deviation, which is less than 1 over k squared. So that is a mathematical proof. It's a very tricky, like really smart proof of inequality. So we start with something that definitely will have that inequality relation and apply the definition itself to make the equation even less relaxed. So eventually we end up having this equation. So in the process of proof, you can see if there's steps where we are relaxing the equation from bigger value to smaller, to even smaller value, which end up getting this. That's why this probability is not equal to this, because along the process, we did a couple of changes to relax condition. But it's still a very useful relation to discover. Okay, so having that, let me try to write down this relation, which says that probability x minus mu to be bigger than k times standard deviation is small. Probability x minus mu to be larger than k times standard deviation. We measure standard deviation, like 1 standard deviation, 2 standard deviation, using a k is less than 1 over k squared. Here, k should be like larger than 1. So you cannot make k equal to 1. I mean, if k equal to 1, this inequality really, it doesn't really bring any information, because probably less than 1, I mean, it's natural, right? Probably if anything is less than 1. So that's why we don't want k to be 1. Anything bigger than 1 is useful. Okay, all right, using that, we also have the opposite, the other side. The opposite of this was saying that probability probability x minus mu to be less or equal to k times the standard deviation. And if you want to calculate this, you might want to calculate the opposite. So if you change this to a less, so that one is small, so of course this one will be bigger. So it will be bigger than what? Bigger than 1 minus 1 over k squared. So as we change from this equation to this equation, this inequality is flipped. This inequality is flipped, and that value is flipped to the opposite. So the probability has been converted, and you have to see the implication for both inequality is slightly different. The top one is indicating there's very small probability outside that boundary. And this one saying there's a big probability within this boundary of k standard deviation. On the board, we have a corollary. And why do we have that corollary? Because this boundary of k x minus mu less than the boundary k times standard deviation, we're using k times standard deviation as a boundary for x minus mu for a distance, meaning that x minus mu is less than this boundary. So sometimes we want this boundary to be a small free variable instead of having to be restricted on k times standard deviation. So instead of that, we can use epsilon. So thinking about k times standard deviation being an epsilon, so k times standard deviation equal to epsilon. So we make that change. If you make that change, you have probability x minus mu is less than epsilon, all right, and then it's less than k. So what exactly is k? According to this equation, k times standard deviation is epsilon. So then k equal to epsilon over standard deviation. So it's going to be epsilon over standard deviation. This rooted by that inequality. That's how we get that one. And then it has to be squared. So because k has to be squared, this has to be squared. So then you can see where that inequality coming from. It's from the original inequality. Let me see if I made it wrong. Right, so it should be yeah, I was like, we must made a mistake. It's bigger than it's like having the wrong direction of my notation. Any question? Okay, so this one, it has a benefit, no more k. We don't care how many standard deviation, we're not counting things with relation to the standard deviation to begin with. But then, of course, your boundary is measured by the division of this, the variance. Okay, so this one obviously is more applicable. All right, I hope I kind of gave us some idea on the Chebyshev theorem. Any question? All right, so let's look at a right, I think that one I mentioned it already. I have this inequality. The direction of the inequality can change from bigger than to less than. So I think those we have already had it on there. Okay, so let's look at a little exercise. So this is the example one in the book saying that suppose x has a mean of 25, variance of 16. And so therefore, standard deviation is 4. We're going to find the lower bound for x between 17 and 33. All right, so let's try to slightly change the question to identify how do we solve the question. So first, we will work on the inequality. And inequality says x is between 33 and 17. We're trying to look at the relation between the x and the mean. The question says the mean is 25. So we got x minus 25 is between 35 minus 25 is 8. 7 minus 25 is negative. So from the same equality, you realize x minus 25 is between 8 and negative 8. As a constant case, we say x minus 25 is less than 8. Right? Are you okay? So that's our equality. So we're trying to look for this probability that x minus 25 minus 8 is less than 8. So we're trying to find out a boundary. It says here, find a lower bound for this. So we're saying this could be bigger than what number? So essentially, we're trying to answer this. All right, we're answering this question. All right, then that reminded us of the Chebyshev theorem. According to the Chebyshev theorem, probability that x minus mu should be less than epsilon that probability is large, right? This probability within it's middle probability. So this is middle percentage supposed to be large. So it's larger than 1 minus epsilon squared over standard deviation squared. I'm trying to refer back to the Chebyshev theorem. And that should be the appropriate lower bound that we're supposed to calculate. So then there's a question, which one is the epsilon? According to the match, the 8 is the epsilon. So then this boundary would be 1 minus 8 squared over the variance. In the question, the variance is, well, is 16. Did I write? 1/4. Right, I thought that will be epsilon, but in the board it's 2 times the division, but it should be the same. Please me. Okay, I think I had it opposite. All right, let me try to. So I had the formula. Okay. So what was the original Chebyshev theorem? It was probability x minus mu less than k times the derivation. All right, which is larger than 1 minus 1 over k squared. Now, if the epsilon is k times standard deviation, then k is equal to epsilon over delta, right? So I don't know who was. Something. Do you notice any mistake in the logic? Yes. So it's k over epsilon, but here we're not doing k squared. We're doing 1 over k squared. So this is supposed to be 1 minus. It has to be upside down. So it's 1 minus delta squared over epsilon squared. And that was my mistake. So this is 1 minus delta squared over epsilon squared. I have it upside down. That's why in my head I was looking at that number. It's not working out. So we have 1 minus the sigma squared is variance, which is given as 16. So here we have 16, and then we have epsilon is 8. So there I'm putting in 8, and we were supposed to square this. So that's epsilon squared. So altogether is 1 minus over 1 over 4, which is 0.75. The solution is already on the board. I was just trying to carry out my own calculation of it. Any question? I hope it's okay. Are we okay? All right, so that was one of the example. There are other example you can find the upper bound for if you switch the direction to a 12, and then we can finish the calculation with a similar procedure. And I had a little example just to compare. This is actually one of the homework questions. I was hoping to provide example that will help you when you are doing your homework. So this is question 6 in the homework. I actually worked out the process. The question have a x bar is a mean of 20, mean of 15 number, and the mean is 80. The variance is 60. We're trying to use Chebyshev's theorem and Chebyshev's inequality to find a lower bound for this probability. So I don't know exactly what is a probability because we really don't know the distribution. We only know this x bar number. So here are the idea of it. First, want to subtract the mean, subtract the 80s. Minus 80, minus 80, minus 80, when I'm having 5. So I realized this is really a calculation for x, that's x bar, right, minus x bar minus 80 is less than 5 because we're calculating probability x bar between those. So in order to calculate probability of absolute value, x bar minus a mean less than number, that calculation reminded us of the Chebyshev theorem. So here I called the Chebyshev theorem saying that you're going to calculate probability x minus mean less than epsilon is bigger than 1 minus delta squared over epsilon squared. So just make sure there are not using the wrong formula. Copy down the formula right there. And then we'll try to pair them together. So now we are applying the formula. All right, in order to apply formula, we have to know the right number, the mean, the variance, and the epsilon are three of the key value in order to apply the formula. So when you look at formula, you look at what you can calculate, and you realize that we have to know the distribution of x bar. So applying central limit theorem, x has a mean of 8, variance of 60. So according to central limit theorem, x bar have a mean of 80, and the variance is population variance divided by the sample size, 60 over 15, which is 4. All right, and then this is what we mean to calculate. We want to calculate x bar minus 80 less than 5. So the 5 is our epsilon. It's epsilon. So we have the epsilon, we have the sigma square, we also have the mean. The mean is 80. So this plug in epsilon equal to 5 and plug in the delta square equal to 4, because it's the sigma square. Sigma square is supposed to be the variance, but it's a variance for the x bar, not variance for the original data, because we're calculating probability about the x bar. So you have to know the variance for x bar itself. So that's the variance, and that's the epsilon square. So this is essentially 1 minus sigma square over epsilon square. The whole calculation give us the answer 21 over 25. And that's the answer for question 6. Any questions? So the whole idea is being able to connect one of the formula, apply the formula really carefully. Obviously, you see sometimes I switched the fraction was applied incorrectly because I copied down the wrong formula. All right, let's extend that a little bit. We were talking about using the Chebyshev theorem on the binomial scenario. So if you have a binomial distribution, y is a variable that's following binomial distribution, then y over n will be the so-called relative frequency of success. So y over n is a probability estimating the proportion p. Okay, so what happened will be y, according to central limit theorem, y over n is normally distributed with the mean being the p. So this is our variable, the p is the mean value. And then the PQ over N will be the variance. So according to central limit theorem, according to the Chebyshev theorem, we have our variable, the mean, and the variance of the variable. Okay, y over n is the variable. P times Q over N is the variance. We apply Chebyshev theorem. So right here we have probability of this bigger than epsilon is less than the variance over sigma squared is now PQ over N over sigma squared. So that will be the formula. And so that will be how we will apply Chebyshev theorem if you have a binomial scenario, because in the binomial case, we have P, we have Q, we have a sample size. It's kind of different than when you don't, for other distribution, we use X for binomial distribution, we use Y over N. All right, and the opposite of this is if you switch the direction of the equality, switch to a less than, then the equality switch to a bigger than, the probability is 1 minus PQ over N times epsilon squared. And this one, when the N goes to infinity, so that's just what's interesting is that when N goes to infinity, PQ over N goes to 0. So the probability for Y minus N, Y over N minus P less than any small number, that probability actually is 1. Okay, and for this we have a terminology called convergence in probability. Convergent divergent is very popular notion in calculus. We talk about limit of this, limit of that. When the limit exists, we say it converges. Now here we see the limit of the probability exists. And that's what we call converge in probability. So we're not saying the function itself converge. We're saying the function, the probability of that function converge. So it's called convergence in probability to value p. And that is proving that y over n is a good estimator for proportion p. Any question? So this is assuming that we don't know the underlying proportion, and we're using 1 over n as a way to estimate its value. Right, so that brings out the notion about converging probability, and that kind of compared to all the convergence in calculus that we had. Right, this theorem is called the law of large number. Says sample mean convergence in probability to mu. This is based on the Chebyshev theorem, limit of probability x minus mu bigger than epsilon. equal to 0. So basically, X bar and mu is getting closer and closer together to the point it won't be bigger than anything. The probability for it to be less than epsilon is equal to 1. So that's converged in probability. Basically saying the more sample size that you have, the closer X bar is with the underlying population. So X bar and mu is getting closer and closer together as the sample size increases more and more. And this is being called the law of large numbers in question. Looks like our time's up. That will be it for today. So this is 5.8. I hope that you can start looking at the homework that we are assigning. There's only 4 assignments, which is 2, 3, 5, and 6. Right, that's it for today. Thank you. I hope that the quiz is still open. If you haven't submitted, you feel free to submit your final version of your solution. That will be it for today. Thank you. Sorry, it's a bit I feel like you've got a lot of time for the quiz, so I don't have a lot of time for this. Question? Yeah, I think it's fine. Assume the, yeah, I think that will be okay.
This one segregation.
Yeah,
I make sure you include the distribution.
okay. Good. Yes.
Probably actually, I didn't know that it wouldn't be on paper, so I was actually able to do it just fine. So I don't think you'll have to send the questions to the
Okay.
testing center.
We finished the question?
Yeah.
Not too much. There's only
Yeah.
2 questions. You were able to complete it.
Yeah, I thought it was gonna be a lot more, but it was,
It's, we're doing a small quiz every Wednesday. I try to leave the whole class
Yeah.
open. So we do have sufficient time. If you don't mind me talking,
Oh, yeah.
I did.
Yeah.
So I was trying to capture the time, but also the quiz plus the class time, the quiz plus the room time on every Wednesday. Yeah, so that way I don't have to submit the quiz to
Yeah.
the testing center. What
Yeah.
about quiz 1? We had a quiz.
Quiz 1, right, possibly, yeah, because I wasn't here, but yeah, I can probably schedule that for, maybe Monday,
Okay.
maybe. Yeah.
Good, thank you. And this way we actually save a little bit of time because I was worried about what you're gonna do during the quiz period of time. So we'll try and see. If you feel like that day is a little bit short for you, then I can submit it. If you're okay during the class, we'll do it during the class.
Yeah, that would be awesome.